Today, we are going to discuss rational design of materials, and within this topic, we are going to discuss two subtopics. First of all, we will be discussing descriptors of materials and how they differ from descriptors of molecules. And second, we are going to consider several case studies that I find exemplary in this field. And then we will discuss some recognized issues of machine learning and chemistry that relate to the field of materials chemistry, to the field of applied machine learning in materials chemistry, especially. So, rational design of materials based on machine learning can be is now a very pursued aim, and there are many reasons for that. So the number of studies related to applied machine learning in the field of materials chemistry grows, and now it grows basically exponentially. I suppose someday we will see the end of this exponential growth, but for now, the growth continues. And the reason for this growth is that the development of materials with optimal properties can be rather expensive, just as in the case of drug design. So the advancement in the field of applied machine learning in the recent years is the basis for this growth. So, first we need to discuss how materials differ from molecular compounds, and we have discussed previously that for any state of matter, there are adequate descriptors that can be features in machine learning models. And taking the fact that materials are often crystalline compounds, or at least they are solids, we need to select descriptors accordingly. So mostly, if we consider crystalline solids, we can speak of molecular crystals, and of course, this will have more similarities with the cases we have discussed previously. And there are atomic crystals and ionic crystals as well. And as the basis for descriptive construction, we can take the concept of unit cell. So because of that translational symmetry of crystals, we are mostly interested in the some kind of an elementary unit. So it will be a unit cell. And as the simplest way to consider solids, we can use some kind of one-hot encoding, so we can encode what elements are present in the unit cell, and in such a way we can describe elemental composition in a mathematically processable way. We can include different stoichiometric numbers. And if we consider unit cells, then we may want to describe atomic properties in this unit cell somehow. So how can we do that? A simple way would be to use the so-called representation matrix. This matrix encodes the features of the atoms in the given unit cell. So if nx is the number of features of each atom and Na is the number of atoms, then we can construct such a matrix in which we encode features and numbers. So by including matrix elements. And what can we do if the number of atoms in a given unit cell differs? So we have constructed these representation matrices.
Question.
Yeah.
What does the power of xe matter? It is the scalar product, or it is
it's an index
the
only.
notion? Okay.
It's the index only. So in such a way we encode. So if nx is the number of properties of features, then we include feature 1, feature 2, and then to nx. And we do this for every atom. So this is for this row is for the first atom, second, and nth atom. And we need to account for variable number of atoms. So we can do this by computing statistics. So we can calculate mean values, standard deviations, skewness, and any needed statistical parameters averaged among atoms in a given unit cell. Then we can combine selected features and compare different crystal cells in such a way. And we can include different atomic properties as features. So there are some features that are listed in the reference book. So we may want to use a relative position. So we can include atomic numbers, charges, atomic weights, or valence states. Of course, we can include ionization energies and electron affinities that are related to electronegativity. And we can include properties like van der Waals or metallic ready, and many other properties can be included in. And of course, we can even use force field parameters in such a matrix descriptor of a unit cell, can we treat solids? Can we represent solids as graphs? And there is an approach that to do that was proposed recently, and you can follow. I suggest you reading this article, which represents this approach in more detail. So if we given a crystal structure, we can use the so-called Voronoi tessellation. And basically, during this procedure, we partition the space in such a way that points around the selected here atoms are assigned to a particular atom according to the fact that they are closest to it. So all these points are closest to this atom. These points in this region are closest to this atom, etc. This is a general mathematical procedure, and it's used in many fields of science. So it can be used in this field here as well. So in such a way, we partition the space in a given crystal cell into regions assigned to atoms. Next, we can search for neighbors. So we then can connect neighboring atoms, and in such a way we get an infinite periodic graph. These can be decomposed into fragments if we are interested in node properties or edge properties, or even in path fragments. Of course, in this step, we can assign features to atoms or edges, for example. And this is done in many applications that I will mention further. And we can also use, we can also consider polyhedrons to represent atomic environments. Such an approach can be used in training of graph neural networks. So you can follow, you can read the referenced article as well. And here I need to mention about, molecular mechanics and force fields. We have discussed this computational approach in several previous lectures. And as I've told you, force fields are basically the force fields are combinations of potential functions and parameters for them that were determined on training data sets for particular elements in particular valence states. So we can we can optimize a force field for carbon atoms, and accordingly we need to account for sp, sp2, and sp3 carbon types, and probably we even can get into more detail by assigning different carbon types to sp2 carbons in double bonds, in linear double bonds, and in aromatic cycles. So all these, so potential functions and parameters combine into a force field. And usually, traditionally, force field optimization was done by using extended data sets of experimental or computational data in which researchers took training systems from the training data sets. They took atomic positions and selected potential functions and potential parameters that upon optimization allowed them to predict system energies or even different properties with the lowest possible error. Usually, force fields were optimized to predict energy, and this is simply because many other thermodynamic functions can be computed if we know potential energies of interatomic, intermolecular, interatomic, and intermolecular interactions, etc. And we can get simulate molecular dynamics by knowing potential functions. So all these could give us the so-called potential energy surfaces that describe molecular reactivity, chemical reactivity. However, recently a new approach was proposed. So a neural network can be used as the as a surrogate of a force field. So in this case, we need to describe systems' atomic and molecular structure somehow. So we need to get local structural parameters, and we need to train an artificial neural network that after the training also gives us system energy, total energy of a system. And in such a way, we get potential energy surfaces as well. So why should we do that? The reason is quite simple. Usually, accurate simulations of materials with quantum chemical methods are really computationally expensive. So we would like to predict materials' properties accurately if we, by knowing material structure on the atomic level, and basically if we can emulate physical laws governing all chemistry, we would get a perfect machine learning model. So even in 1929, Paul Dirac stated that all physical laws governing chemistry are completely known. However, all these physical laws about which Paul Dirac made this statement related to quantum chemistry and quantum mechanics, including relativistic quantum mechanics. And all these computations can be really expensive. So if we take more and more accurate methods that predict energetic parameters, for example, with higher and higher accuracy, we get the computational scaling gets worse and worse. So these ends are roughly the numbers of electrons in a given system. Of course, getting O from n in the nth in the seventh power is really rough. And by using machine learning, researchers try to get machine learning models that predict energies with the accuracy comparable to best quantum chemical methods that scale as molecular mechanics force fields. And sometimes it's done successfully. So there are many examples of studies of this type, and you can follow. You can read this study. There are some pros and cons related to such an approach. So these ML force fields are very cheap in terms of CPU time. However, this approach is empirical. So basically, it has a limited domain of applicability unless we emulate laws of nature exactly. However, it can barely be accomplished without if we aim to reduce computational cost. And we are going to discuss several descriptors that are used in this atomistic machine learning. I have mentioned previously the Descript library that allows us to compute several atomistic descriptors. The first one is Coulomb matrix that we have computed on several examples. So basically, it is defined in this way. There are diagonal and non-diagonal elements that emulate electrostatic interactions, although you shouldn't consider these approximated numbers as real electrostatic interactions in model systems, of course. And there is a significant problem with Coulomb matrices because so it's caused by the fact that electrostatic interactions converges poorly. Here we have the interatomic distance in the first power. So electrostatic interaction decays very slowly with the increase in interatomic separation. And in crystals, this can be a huge problem. A known remedy for this is to use the eval technique. So we can compute an eval sum matrix in which real electrostatic, the so-called real part of electrostatic interaction is combined with the background part. So here we can compute the real part by accounting for interatomic distances in a periodic cell. And next, we can compute the background part that doesn't have any that does not depend on interatomic separations. There are also parts for the diagonal elements and for the so-called reciprocal part. So by computing all this, which is done automatically by using the Descript library, we can get such a matrix that can be a descriptor of atomistic structure. We can also use we can also use sign matrix, which has no physical interpretation, but it captures some properties of electrostatic interaction. And this is defined in this way. So here we have the similar matrix diagonal elements, and here we have elements, the non-diagonal elements depend on interatomic distances. We can consider the so-called SOAP descriptor, which stands for smooth overlap of atomic positions. It is power spectrum of this vector, which is given by this formula. Although it looks complex, it can be computed automatically, and it is basically similar to some instruments, to some models used in quantum chemistry. So these coefficients consist basically of 3 parts. First of all, they include the so-called radial basis functions. By default, Gaussian basis functions are used. Here we can refer to this formula on the Wikipedia. So we have exponents in the second power that depend on the radius from a given nucleus. Next, we can spherical harmonics are included. These combination basically resemble atomic orbitals, and atomic orbitals in hydrogen-like atom also consist of a radial basis function that can be of Gaussian type or Slater type, and spherical harmonics. So radial basis functions in atomic orbitals or in SOAP descriptor can have nodes, and next there is the part that is dependent on atomic positions. So all this is computed automatically, and you can tune hyperparameters like angular momenta, like parameters of radial basis functions and spherical harmonics, and also of sigmas. And also you can optimize sigmas for your training data set. All this you can do by using the Descript library that we have mentioned previously. There are other descriptors that can be computed, and we are going to focus on Coulomb matrices, and so that we will use these two descriptors in the upcoming workshop on modeling, on the prediction of formation energies, crystal formation energies. And we are basically going to replicate with some minor differences the use cases that were provided by the authors of this paper. So in this paper, the Descript library is presented, and the authors considered machine learning models based on Laplacian kernel-rich regression for prediction of formation energies. So they compared several descriptors, and the SOAP descriptor with optimized hyperparameters offered the best accuracy. There are other descriptors that can be used to represent structures of condensed matter on the atomic and molecular level. One of the classic descriptors is radial distribution function. Such a function basically gives us density variation on moving from a reference particle. So if we consider a liquid, a Lennard-Jones liquid, then under some parameters, the radial distribution function would look like this. Upon moving from the reference particle, we get the uniform density. So we reach 1, and we get maximums and minimums. So basically, around a reference particle, we can get 3 other particles, for example. And of course, it depends on the normalization, and pay attention to the units that are used here. But anyway, given such a function, we can get info on particle atomic environments, including distances and the numbers of atoms that are in such an environment. Of course, we can integrate these functions, and it is done in some studies. However, it's beyond our scope. We can have a dielectric with separated conductance and valence bands. We can have metals with partially or fully filled valence bands and the partially filled conductive bands, and we can have a semiconductor with a relatively small band gap. This is all. These parameters of electronic bands can be used as features if we want to describe some element, some material properties. And if you are interested in electronic band theory, I suggest you this book that gives a soft introduction in the topic. So here we are interested in band properties. Why this can be? First of all, we may be interested in the band gap if we study, if we model some semiconductors. However, there are some properties of electronic bands that are related to adsorption, for example. And the most frequently used is the so-called D-band center. Often materials interact with adsorbing atoms or molecules with d electrons. So basically, electrons from the d band interact with antibonding and bonding orbitals of an adsorbate. So this d band center allows us to estimate, or roughly estimate, how strong will be the interaction with either bonding or antibonding orbitals of an adsorbed atom or molecule. And this D-band center descriptor is often used in materials, in studies of materials or catalysts. However, considering an ideal crystalline solid can sometimes be not enough. So some materials, properties of some materials highly depend on defects on its surface. And if we consider carbon materials, adsorption on carbon materials to be exact, then we may be interested in the distribution of grain boundaries or some surface defects, because, for example, palladium or many other metals are adsorbed on the carbon surface non-uniformly. So palladium and some other metals cluster in the defect regions, and basically adsorptive properties of carbon may be highly dependent on the distribution of defects and their type. At the same time, if we want to consider a catalytic system like this one, so palladium and carbon, we are also interested in the surface morphology of the catalyst, because catalytic activity is due to the properties of surface atoms, not some in crystal buried atoms. And there are several classifications of structural defects in crystalline solids. Which descriptor would you propose to account for defect sites on a crystalline surface? I would propose to use surface density of defects. And also I would propose to, I should mention several review articles that I can suggest. So I would suggest 2 review articles. The first one is a good introduction into the topic of applied machine learning in the material science. And next, you can refer to this perspective article if in case you are interested in recognized issues or problems in the field. So let's discuss 3 case studies that I find exemplary. First, there is a study that highlights the problem of material science related to practice. Basically, development of materials can be costly, and there are some material properties that are related to their use. And if we want to develop batteries, there is one property that every user values, at least among the most. It is durability. Used simple machine learning methods like so they use regularized linear regression, and they analyzed voltage curve characteristics to use them as descriptors to predict characteristics of battery life cycle. And this, of course, is a rather simplistic approach. Here we have no relation to, we have no info on atomic structure. We only have properties of curves like height. However, it was such an approach was successive, allowed them to successfully predict battery durability that is very expensive to test experimentally. The second study addresses the practically important question of the dataset size. It's usually very hard to construct a large dataset that is representative, and dataset construction can take, or dataset curation can take the most of the time of a project. And at the same time, the increase in accuracy for machine learning models is rather unsatisfying. So if we increase the size of the training set, upon some increase, we can get a very minor increase in accuracy, as authors of this paper state. And they proposed to increase model accuracy by incorporating coarse calculated properties. So basically, what they did is that they computed the same material property that is predicted with a machine learning model with an approach that is cheap in terms of computational time. For example, they used low-level quantum chemical methods to compute band gaps. And this worked well. But before that, let's mention that they used several simple descriptors to as features in machine learning models. So they used stoichiometric attributes, elemental properties, just as those that we have mentioned previously in this lecture, like van der Waals radio, covalent radii, element numbers, etc. And they use simple compound descriptors and electronic structure parameters. So they selected particular descriptor set on the case-by-case basis, depending on the predicted property. What's important that the inclusion of the same property they modeled as a feature of the same property computed in a coarse way allowed them to increase accuracy very substantially. So they computed band gaps, they predicted experimental thermal conductivities by using an empirical model, and they used molecular mechanics force fields to compute bulk moduli of zeolite materials. And especially in the last case, they obtained a twofold increase in model accuracy in the percentage scale that was determined by cross-validation. And they used kernel-rich regression and gradient boosting. So you can refer to the original article if you are interested. And before this point, we have discussed mainly studies and descriptors that consider atomistic structure of materials. However, in some cases, we can predict material properties with high accuracy, being ignorant of crystal structure at the same time. So the authors of this paper used graph neural networks to predict formation enthalpies of materials and band gaps. And follow this link for a simple introduction into graph neural networks However, as long as this topic is beyond the scope of our course, I leave this to suggested reading. Mentioning this study, they represented materials as connected graphs with vertices representing elements in which they encoded features of elements in a given material. So upon the message passing, properties of vertices were updated according to a pre-selected algorithm. And so basically they used dense weighted graphs to encode information on materials, to represent materials. And they obtained quite high accuracy that is better than the accuracy of many quantum chemical approaches, DFT approaches to be exact, in the prediction of band gaps, for example. And at the same time, the model was basically ignorant of the crystal structure. So this, for me, for a chemist, this quite I was quite astonished to see this, but it works actually. So there are many properties of materials that were predicted using machine learning. And while early reports are from 1990s, in the recent years, the number of studies has risen very substantially. And even even properties related to defects can be predicted by using machine learning. Of course, there are many other properties like band gaps or thermal conductivities, thermal expansion coefficients, etc. So you can find a review here in this paper. And there are some issues that we should discuss, the issues related to machine learning, to the application of machine learning in chemistry and material science in particular. As I've mentioned earlier, unless a model captures physical laws exactly, there is a domain of applicability, of course. So for example, if the model is trained on superconductors or zeolites used as adsorbents with specific superconducting or adsorptive properties, then the model won't be predictive for any superconductors or zeolites, or I would even say adsorbents like carbon materials that differ substantially from the training dataset. So next, there is a problem of data availability. And mainly it's related to the fact that PDF files used to publish scientific papers, scientific articles electronically are poorly processable with natural language processing tools. And this is a problem for many old for articles from the previous years. And in the recent years, this problem is mitigated to some significant degree, I would say, because now there are approaches to store experimental data in electronic lab notebooks, and there are many depositories that can be used to deposit your experimental or computational data. Some of these depositories follow the so-called fair data policies, of which I've told you about in the fourth lesson. So there is an expected problem of data quality, and even small of course, we can speak of malicious data fabrication or malicious data holding that can lead to irreproducible results in the scholarly literature. However, we should also note that in some fields of science, even small variation in experimental procedures can lead to irreproducibility. So some factors that may seem minor to researchers may in fact be significant, and if these factors are missing in experimental procedures, this can lead to irreproducibility. And of course, this leads to the so-called garbage in, garbage out case. Basically, if we have bad data, quote unquote bad data, then we can get a model that makes false predictions. However, here we should also mention that machine learning sometimes strikes back. Some high accuracy machine learning models allow us to highlight outliers in both data in training and test data sets. And these outliers sometimes are the mentioned the bad data mentioned earlier. For example, you can refer to this paper for a case in which artificial neural network trained to predict nuclear magnetic resonance chemical shifts allowed to find inaccurate data in experimental spectra. So there is the usual problem of imbalanced data sets. Negative data are crucial in training accurate models, and at the same time, researchers usually seek to find publishable data. So they aim to get data, aim to have working experiments. This is, however, it leads to the problem of imbalanced data sets, and you can refer to this study. So basically, for some ligand targets, there is a significant imbalance in public data sets like Campbell. And also, we should mention that true rational design of materials is a multi-objective task. So for real-world applications, we usually need to find a balance or even a trade-off between multiple properties. For example, some materials, some new materials can be very can have properties that are outstanding, make them outstanding among competitors. For example, they can be semiconductors or superconductors with very high critical temperatures. However, synthesizing them can be very expensive, or they can exhibit this high temperature superconductivity at very high pressures. So it is it can basically be impractical to synthesize such superconductors, or for example, we can synthesize CO2 adsorbents that are very efficient, however expensive, etc. You name the case. And so real-world applications, for real-world applications, we need to do multi-objective optimization. And we can include even sustainability in the set of desired properties. And also, we should mention synthesizability. That's because we can predict materials, may it be by using a generative model or performing virtual screening. However, all this, a predicted material or molecule can be hardly synthesizable. And for materials, this now is considered as a great challenge. However, for organic substances, the problem of synthesizability prediction is to a significant degree solved. And we are going to discuss this in the last lesson of this course.